I want to show you how we can design, develop, and implement an artificial neural network using some more advanced libraries and tools. Specifically, we are going to talk about Keras and TensorFlow. TensorFlow is an open source library for high performance numerical computation, including machine learning. So machine learning is one of the most important applications. Machine learning and deep learning are most important applications of those numerical computation, and many other scientific applications. It's originally developed by researchers at Google Brain, within Google's AI. So it's an open source and very, very popular library for doing machine learning and deep learning, specifically artificial neural networks. Keras is a powerful and user-friendly and open source neural network framework that is capable of running on top of TensorFlow or Theano. So Theano is another library for neural networks, but Keras is very powerful and very user-friendly. It's an open source, and this is my favorite. So it works very well with TensorFlow to simply design it. It let you design your neural network and then train it very well. So it's very powerful and very user-friendly. So installation is very easy. You need to install these two. If you are a Mac user, just pip install TensorFlow and Keras in your terminal. You can also, if you don't have Mac or Windows, you can see this links for more instruction about the installation. So you need to install and add these two libraries to your Python. So let's open the tutorial and continue this topic. Okay, so again, the references are here for installing your for installing TensorFlow and Keras. Okay, so in this tutorial we will designed, build, and train artificial neural networks with Keras and TensorFlow, and you have to first install it, as I mentioned. After installing that, I am gonna import sequential models. Okay, so sequential models a type of models in Keras that let you define a stack of neural networks in the form of layers, layer by layer. So from Keras models, I import sequential, and then I import the core layers that I want to use. In this example, I'm gonna specifically use dense network, which is also fully connected network. It means that every neuron is connected to every other neuron in the next layer. And activation function, of course, you know, we can use sigmoid or other type of functions. So I import these functions and libraries that I need. Keras would also let you do a lot of pre-processing on the data. So I import this one, MP-utils, some utilities that will help me to transform data, to pre-process and transform data. So in this case, in this example, in this tutorial, I want to use images, and specifically I'm gonna use MNIST. You are familiar with MNIST from before. So it includes 70,000 images of handwriting digits. So the size of the data is pretty large. Usually 60,000 of that are designed for training set and 10,000 of that for testing set by default. And the size of images are small, which is good for testing your model and training it fast. So it's only 28 by 28 pixels, but the size of their data set is pretty large. So I import this data and it is already embedded in Keras. So I just import this from, I just read it, I just load it from my from the Keras data sets. And if you check the size of that, you will see that 60,000 of those samples are training and only 10,000 of them are testing. And the size is 28 by 28. So as you see, this is your training data. As you see, it is 3D, right? So this is the number of samples and this is the size of the sample, 28 by 28. So in other words, it includes 60,000 pictures. Each one of them is 28 by 28. Each picture is a feature. Each pixel is a feature for your machine learning algorithm. Remember that. Okay. Now I want to see some of those samples. So I just use matplotlib to see some of these samples. I use this matplotlib to show some of these samples. So this is 5049. So these are just handwritten digits, and we want an algorithm, a machine learning algorithm, an artificial neural network that can detect these digits. Okay. So this is an easy task for our brain, as you know. Well, even sometimes for our brain it is difficult. When you see a number, for example, on an envelope, sometimes even it's challenging for us. We cannot recognize if it is, for example, 1 or 7. Okay. But we want to develop a machine learning algorithm that does that for us. And as I mentioned before, this was one of the very most important and one of the very first applications of convolutional neural network and neural networks in general. USPS specifically wanted to make some automated system for reading the envelope and address and zip code and so on. Okay, so let me continue. I reshape these images into each image into one row of my feature table. Okay, so each image is 28 by 28 pixels. Each pixel is a feature, so 28 times 28 will be 784. So I have 784 features for each data sample, for each picture. So I reshape a 28 by 28 2D image into 1 by 784 row. So I put all of the pixels next to each other to make one row of my feature table. You can do it with this method, reshape. So if I run it on both training and testing data and then print it, this will be our data now. So I have a feature table with 60,000 rows and 784 columns. Each column represents one pixel of the picture. here I just normalize those values. So the value, this is grayscale. So the value is the value of each feature is it's a number between 0 and 255. Well, I just divide that by 255 by the maximum value to make all of them in the range of 0 to 1. And then let's take care of the label. So your output, your label, of course, is a number between 0 and 9. This is what you want to predict. You want to detect if this is 0 or 4 or whatever. So your output is one value in the range of 0 to 9. But as you remember from before, let me see what lecture. Yeah, here you go. So in neural network, unlike many other machine learning algorithms, you can have various outputs and you can do one-hot encoding for your output. Okay, so rather than having like one output that gives me 0, 1, 2, 3, 4, 5 or to 9, I can do one-hot encoding for the output so that this represents 0, this represents 1, this represents 2, and so on. So now, so then your neural network will have several outputs. So I am gonna do that here, and Keras is again very powerful. Okay, it has a method from this module. It has a function called toCategorical that will do that for us automatically. So after that, this is what we have. Okay, so for example, this first sample is 0, 1, 2, 3, 4, 5. So it represents 5. And here you go. This was the 5. So the second sample is 0 in my data set, and this is how I show 0. The third one is 4, and this is how I show 4, and so on. So I do one-hot encoding for the output. So it tells me that your neural network will have 10 outputs. Remember that. 1 for 0, 1 for 1, and so on. Any questions? Okay, so let's continue. I want to define the network architecture now. So please listen carefully here. I defined a sequential model. As I mentioned, I call it model, whatever arbitrary name you can select for your neural network model. As I mentioned, it's a sequential in the form of layer by layer. This is what we want. So these are the size of the network. First of all, we have 784 features, right? Because we have 784 pixels, 28 times 28. So these are the number of inputs. Each pixel will be one input. And then I have 10 outputs, of course. I just talked about that. These are my output of the network. And I have 100, I want to use 100 neurons. So one hidden layer with 100 neurons, okay? So only one hidden layer, so it's not too deep, but there are pretty good number of neurons in that one hidden layer. So I define these parameters for the structure of my network, and now this is how I define my network. So first layer, it does not need anything. It has this number of values, and first layer actually is just input layer. It does nothing. Second layer of your network will be your first hidden layer, and this is how you define it. So as you see, this is much more flexible compared to scikit-learn. So the scikit-learn was very limited in defining the structure of the network, but this one is much more flexible. I add, so your model that you just defined here, I add a dense layer. So dense layer is like a fully connected layer, neurons connected to each other. This is what we want. And these are the values that I defined for this. Okay. The number of hidden layers that I want is 100. Okay, so here you go. So it includes 100 neurons, and the input of that is, this is the size of the input, 784 different values comes to this 100 neurons. Okay, so you define the number of neurons and the number of inputs for that, and then I add an activation function sigmoid after this. Okay, so here if you notice, I add a neuron first and then activation function, but in scikit-learn both of them were together. You added them in the same step. And by the way, you do it individually for each layer. And then our last layer will be our output layer. It includes, here we go, 10 values. And the input of that will be the output of previous layer. So this is the input dimension, which is 100, because the input of that is the output of the hidden layer. And then for activation function, I add a softmax activation function. So softmax is a function that also somehow represent the probability, but for more than one variable. Okay, so for more than one output. This is a very, very useful function, activation function, when you have non-binary outputs. So when you have binary outputs, you can also use sigmoid function for your output. But when you have non-binary output, like this case that we have 10 outputs, we usually prefer softmax, okay, for your output. So this is a perfect function when we have non-binary output. Okay, I just defined my network. I have to compile it before training. By compiling, then the structure that I defined here will be created. Okay, so by doing this compile right here, you create the network. Now I have created the network. It's not trained yet, but we build it. And right here, you can define some parameters. So, for example, you can define your loss. This is the cost function that I talked about. And categorical cross entropy is, so you can check the list of those. So this is Keras documentation, which is pretty comprehensive and nice. And you can see a lot of different things here. So for example, you can check the different loss functions that it supports. Okay, so these are many different loss functions. And categorical cross entropy is similar to the log function that I defined in the class for the cost function. Okay, so when you say this, it will create that function as your loss function or cost function, and it will use this to minimize your model. The metric to consider for validation is accuracy, and optimizer is Adam, which is a type of stochastic gradient descent. So this is how you define what algorithms you use to train our neural network. And then the process of training is similar. You just use fit method. So I run it. Okay, so before run it, let me explain some of these parameters. Again, it is much more flexible compared to scikit-learn. It gives you more flexibility, and you can also check the Keras documentation for more details about the inputs that you can provide. But simply this is X-train and Y-train that we use for training. We can have validation split. If we do that, the algorithm will, in this specific case, the algorithm will assign 33% of the data for validation. It doesn't use it for training, it just uses it for internal validation to figure out when to stop training, for example, and some other applications that I'm going to talk about later. Batch size is another parameter that you can adjust. So batch size, if you remember from last semester, I told you that in batch gradient descent, rather than providing the entire training data set to take one step of gradient descent, we can provide a batch of data, for example, some amount of samples in each iteration, in each step of gradient descent to your gradient descent to take one step. So in this case, I define 32. It means that to take each step of gradient descent toward minimum, it should use only 32 samples. So we provide training data to your network in batches of 32, in fact. Epochs is another parameter. Epochs means the number of times the algorithm in the training process, it goes over the entire training set. Okay, so when epochs is 15, it means that in the process of training, you tell your algorithm to go over the entire training set 15 times. So it's important to understand the difference between these two. 32 means that in each step of gradient descent, I provide 32 samples of training. So I provide samples of training to my algorithm in the packages of 32. But epochs is the number of rounds that the algorithm goes over the entire training set, 15 rounds of training. And this parameter just tells you, do you want to see the process of training or not? Okay, so again, I provide some information here. So let me run it, and it is training now. Okay. So 15, my epochs was 15. It means that it goes over my training data set 15 times. Each one of them is one round. Okay, finished. So now look at here. I have loss value again. Look, in the first round, the loss was 0.8, which was high. And as we move forward, the loss value is smaller and smaller and smaller until it finally reaches, after 15 epochs, it reaches this value. Okay, this one gives you your accuracy on the training set, which is very high, not surprising because it's accuracy on training set. But this value is the loss and accuracy on validation set. So you remember I used 33% of the data as validation. So this part is not used in training. It was just used for validation in each round. And so it gives me 99% accuracy on training, but 96% on validation. So this is the process of training, and it shows us all details. Okay, so here there are some techniques to stop early if you want. There's something called callbacks. Okay, callbacks are the techniques in Keras that let us, so again, you can read the details, but if you are interested. But there are some techniques that let us do different tasks in the process of training, in the middle of the process of training. For example, here I used early stopping. It means that this is something similar to what we just saw in scikit-learn. Okay, so early stopping let us, using this line, it let us check, for example, validation loss, this value, validation loss. It checks in each round, and this too means that if for 3 consecutive rounds the value of validation loss didn't change by this number, then stop. Okay, so patience 3 means that for 3 times you can tolerate less than this value of error. And so this is a good way to stop early when you feel that your network doesn't learn anything anymore. So rather than having 15 going all the way to the end of the 15 rounds, it can stop earlier if it feels that it doesn't learn anything anymore. And now here I want to show you something. I will talk more about this later, okay, in deep learning, when I talk about deep learning, okay. But that's a very good thing to remember. So because one of you asked about what other techniques we can use other than brute force. So technically we can always, so these are the things that I talked about before too. We can plot these two curves, and one of them is your loss on training, the other one is your loss on validation or testing. Okay, and usually your loss on training is always decreasing, because the more you train, the more accurate model you make on training data. So this curve is always decreasing. But this orange one, which is your error on test, it is decreasing to some degree, and after that it's getting flat, and after some level it's going up. So it means that after this level you are making your network too complex and overfitting starts happening. So this is the time to stop. So we can use this idea to find out what range of brute force, what range of search we have to do to make your network for finding hyperparameters. Okay, so for example, you can make your network more complex by adding more neurons, okay, in each layer, and adding more hidden layers. But we cannot search every possible situation, of course. We can only search in the range that this orange one is still decreasing. As soon as this orange curve is getting increasing, it means that your network is going to overfit situation, and you can stop searching. Okay, so you can make your network more complex as long as it doesn't happen. So by reviewing these curves, the blue one and the orange one, and see how they work, you can know what is the best range for your network and what is the best structure for your neural network without searching every possible case, without checking every possible structure for your network. So on the other hand, for example, this blue one, if the blue one doesn't go down anymore, and it's still upright here and it doesn't go down anymore, it means that your model is not complex enough. It is underfit. And in this situation, you can add a new hidden layer or add more neurons to your existing hidden layers. So this way, you know the structure, what is the best structure for your network, or at least you will know the range of that. So now I know that I need 2 or 3 hidden layers and maybe 50 to 75 neurons in each layer. So I know this, I can learn this based on these graphs, and after that you can run a grid search within only this small range to find the best structure, to find the hyperparameters. So anyway, I will explain these things more later in deep learning. They are more important later when we talk about deep learning concept. And when I run it on testing set, I predict on testing set, evaluate, it gives me the accuracy of 97% for prediction on the testing set, for predicting handwritten digits on 10,000 samples from MNIST dataset.